Okay, so I just got a couple of more topics to cover, so overfitting and regularization, and then I'm going to give you a brief MATLAB demo on how to use the optimization toolbox in MATLAB. Okay, so I'm going to talk about something which is called overfitting, all right? So when I talked about maybe a couple of classes, maybe the first class, I told you that it's a good idea to have as many features as possible to be able to discriminate between, one class or another. So it's good to have as many features as possible when creating the prediction model, okay? But there may be a case where you have too many features. Let's say you've got 200 or 1,000 features, for example. The more features you have, the better it will probably fit the training data. But when you decide to put in a new training example, an example that it hasn't seen before, the model that you created will not what's known as generalize to new examples. And this is what is called overfitting. Okay, so what overfitting means is that usually in your data there's going to be a little bit of noise. All right, so it's not going to be clean to begin with. So if you include as many features as you can, what's going to happen is that those features are actually going to incorporate the noise as part of the model. So it's going to think that the noise is actually part of your training data rather than actually it not being part of your data at all. It's some just anomalous instance, for example. So if the training data, or if the training model that you created, if it incorporates that noise, what's going to happen is that when you provide new instances, and that instance, for example, might be noise-free, it'll artificially introduce noise that was not there before. So it'll actually give you a misclassification, or it'll give you a bad output. All right? So overfitting. Usually, in data sets, there is some noise, right? Using many features will incorporate the noise in the model. Okay, in the prediction model, all right. All right. So for new inputs, the outputs will exaggerate fluctuations. Not meant to be modeled. So this is what is known as overfitting, and the best way to show you is a picture, an example. Okay? So, let's see. Okay, this is also taken from Andrew Eng's slides. Very, very nice guy. Okay, so let me just go to full screen so you can see, where is it? Full screen. There we go, so you can see a little bit. So this is linear regression. So we have this data which is nonlinear, obviously it's nonlinear, okay? And we decide to make our model just one feature, right? Just one feature that is linear, okay? And if you're just doing it as a line, it will look like this. And obviously it doesn't fit the data well. So this is what is known as underfitting. And it's also what is known as having high bias. We'll talk about bias and variance later on in the course, but I just wanted to introduce this so you can see what I'm talking about. This is what's known as underfitting. And if we have a quadratic model, it does look like a quadratic model. So this is just right. Just right. Okay, so it might look something like this. Okay, that's cool. All right? And then if we have a lot of features, we have a cubic and a fourth order as well, this is what we call overfitting. So it will look something like this. Like this, I guess, for example, like that. And these fluctuations are modeled because you have these higher order polynomial terms. And you don't necessarily want to incorporate this fluctuation in your model because new instances, maybe if you were to choose an instance over here, you'd probably expect it to be somewhere over here because the line trends this way. But in fact, it maps over here instead, and that's not what you want. And this is what is known as high variance. Okay? So this is what is underfitting, and this is overfitting. This is when you have too many features, and then the unexplained fluctuations in your data are trying to be incorporated into your model, and that's not correct. You want to avoid those, okay? And then here's another example with logistic regression. So logistic regression, this is, you're trying to figure out the right decision boundary, okay? So this is with logistic regression as well, all right? So remember, so this is the sigmoid function, and let's say we have just, you know, 2 features, and it's just linear. So in this case, with the sigmoid, it would just, you know, with this case, all you're doing is finding the line of separation, the best line of separation, and it might look something like this. And this is, again, what's known as underfitting. It doesn't really do quite well, okay? And then if you decide to incorporate, you know, polynomial features, like you have the squared here, then you also have a product, it might look something like this, and this is just right. Even though there are a couple of misclassifications, what's known as, it generalizes well to new data. So it does tend to fit a little better. So this is just right. Okay? But if you have a lot of features here, for example, here you have, you know, cubic terms and, you know, quadruple terms, it might overcomplicate things. It might look something like this. Right? And let's see here. Where am I? Oopsie. Something like that, I guess. Sorry. Okay. Oopsie, I can't draw. So let me see. Oh. Yeah, there we go, something like that. Yeah, there we go. Okay, and well, that might be nice, but then it doesn't generalize well. This is overfitting. It might fit the, you know, the training example as well, but then it won't generalize for new instances. Like, it'll most likely give you a bad prediction for new instances that you haven't seen before. So there's 2 ways you can combat this. The first way would be, okay, let's try to reduce the number of features. But it's a long and involved process because you have to pick and choose. You have to take out one feature, try to train your model again, see if it fits, and if that doesn't work, you might have to take out another feature and then another feature. So it's a long process to figure out which features you want to take out. Okay, that's one solution. Another solution is to just leave everything there, but modify the cost function in such a way where it'll allow you to put as many features as you want, but it won't allow the model to overfit. And that's a process which is known as regularization. Okay? So how do we address overfitting? Okay? One method is to just reduce the number of features. Oh, that's great, but then how do you know which features to remove? Like, you have to do like a sensitivity analysis and figure out which feature has the most pull, and that takes a little bit of time. All right? The next method you can try is regularization. This is where you don't care how many features there are. You can add as many features as you want, and the point of regularization is that it will it'll make the parameters, you know, a little small. It'll reduce the magnitude or reduce the value of the parameters, where just each one of them will contribute a little bit to the output, so that you can just combine everything all at once and it'll give you a nice, you know, prediction. All right? So regularization, the definition of regularization, you just keep all of the features, okay, but reduce the magnitude or the values of the parameters, or theta j from j is equal to 0, 1, and so on. Okay? So if you make every parameter small, like small enough, then what's going to happen is that each one of them will contribute a little bit to the output. And that way, it'll prevent overfitting because it makes your hypothesis a little simpler to deal with. Okay? So make theta j small so that this reduces overfitting. Okay? And creates a simpler hypothesis. Okay? This works well when there are a lot of features. Seeing how much time I got, good. I should be able to finish up. A lot of features, let's see. A lot of features, and each contributes to, each contributes a bit to the output y. Okay, that's cool. Okay, so how do we do this? What can we do? How do we introduce regularization into this? How do we do this? It's actually quite easy. What you can do is you can incorporate an additional term into your cost function. So introduce an additional constraint into J of theta. Okay? So if you remember for linear regression, the cost function was 1 over 2m, and then it was the sum of square differences. Okay? So this is what it was for linear regression. Okay, so this is the before. With regularization, what you're going to do is you're going to add an additional term, or additional terms. This is lambda. Okay? This here is what's known as regularization. And this is the regularization parameter. So what's so special about this? Okay. Also take note here that I apply regularization to everything but the bias term. Okay, so applies to all parameters. And I'll talk about this in a minute. I'm sorry, except. See? So what this is here is that we have n features. Okay? But notice that the sum starts at 1, not 0. Why is that? Well, remember, the whole point of regularization is to make the parameter small. And the bias term actually contributes the most to the output because it gives you basically the DC offset or the offset, and then each of the other parameters will contribute to the output. So if you made the bias small, what's going to happen is that your prediction is going to be centered around the origin. And if you have a bunch of prediction, if you have a bunch of positive and negative examples that are away from the origin, if you regularize the bias, it's going to bring it back to the origin, and you're going to get misclassifications. So you only apply regularization to all the other parameters except for the bias, which is theta 0. Okay? Because why? This contributes the most to the prediction. Don't make this small. Okay. So now the intuition behind this is that what you're doing here is you're introducing additional costs into your function. So what you're doing here is you are adding the parameter and you're squaring each term. The reason why you're squaring is because it makes the cost function convex so that you're able to apply gradient descent to this. Okay? So square each theta j to allow cost function to be convex. Okay? So you square each term to be convex. So basically what you're doing here is you're adding an additional theta. So what does this do? What is this actually doing? So how does affect our model? So what does lambda do? So let's assume for now. Sorry. Oh, sorry. Okay. So assume that, let's say we have our prediction model like this. So it's going to be a fourth order polynomial. Okay. So let's say I got this. All right. So how does it? So here, I'm going to show you a little bit of a picture. Okay. So I'm going to show you 3 different situations. If we set lambda to 0, what that means is that you are eliminating this from the cost function. So if you set lambda equal to 0, what you're doing is that you are not applying regularization. So you're just doing normal gradient descent. So regularization is not a factor into your cost function anymore. Okay? So lambda equals 0 means that no regularization. Okay? And using normal gradient descent. So if that's the case, what's going to happen is that if you set lambda equal to 0, then there is a possibility that you will be overfitting because you have that many features. So it's gonna look like this again, like what we saw from before. All right. So if I decide to make it a little bigger, right? So this is just a bunch of data. So the features are the size of the house, and then the output is going to be the price. Okay, this is just a random graph. So if I set lambda equal to 1, this is just right. So then what's going to happen is that applies all the let's see here. So what's going to happen here is that a little bit, and I'll give you a summary at the end. Each parameter contributes. So it might look something like this. Okay, that's great. All right, and then finally, if I decide to make the constant really big, okay, let's say, okay, what's going to happen is that if you make this constant very big, what's going to happen is that in order to compensate, in order to make the cost function small, if you sorry. If you make this constant really big, it'll force the theta j to be very small to compensate, to make sure that the cost function is small. So the larger the lambda, the smaller the parameters have to be in order to drive the cost down. So if you have a large lambda, what's going to happen is that the parameters are going to be so small that they're pretty much insignificant. So in that case, these theta parameters, these are all going to go away except for theta 0. And in that case, it's just going to be a straight line. So if you make the parameters very large, if you make this very large, what's going to happen is that parameters will be so small that so small that they are insignificant. In that case, your parameters, right, your prediction model is pretty much just going to be the bias term because all the other ones are going to be small. So in this case, it's just going to do a flat line like this, okay? And this is not good. All right, so purpose of adding to cost is to force parameters to be small when finding the optimal parameters. Okay, so that's the purpose. If you make this term too large, it's going to force the parameters to be small to make sure that the cost function is small. And in that case, the only thing that's left is just the bias term. It's just going to be a flat line. If you make lambda equal to 0, then you're not regularizing anymore. You're just doing normal regression. It's going to overfit. So you have to experiment and choose the right number so that it will prevent overfitting. And usually lambda equal between 1 and 5 is usually a good thing to try out first. Okay, so now that's good. So how do I incorporate this into gradient descent? Actually, before I do, let me just talk about the logistic regression too. So, sorry, let me just go back up here. So for logistic regression, it's pretty much the same thing. Okay, you have your cost, and it's 1 over m. So this is minus yes, and then minus. Let me just bring this down here. Just going to continue it on from here. And it's still multiplied. And then you're just adding a regularization term in. I like to introduce this to be a factor of 2, divided by 2 instead, and you'll see why in a minute. Because when you do gradient descent, it will cancel out. Notice that at the top, so you know this is fine, this is the same thing. This is regularization. Okay, let me just scroll it back up a bit. So if you take a look here, the regularization term, I didn't add a factor 2 here because when you do gradient descent, when you differentiate, the 2 will cancel with this 2 over here. All right? But if you take a look at the logistic regression, there's no longer a factor of 2 here. So I have to introduce it over here so that when I differentiate, it goes away. So the factor here is just allow for mathematical convenience, but it doesn't affect the mathematics. It just allows you to apply gradient descent a little easier. Okay, so that's logistic regression here. All right, so how do we do gradient descent on this now? How does this change our gradient descent? Okay, so how do we find the parameters with regularization? Okay, good. Just want to make sure I have at least 20 minutes to do the MATLAB stuff with regularization. Okay, well that's easy. All you have to do is just find the, just do gradient descent and then just find the derivative with that regularization stuff added to it. Sorry, just frog in my throat. Use gradient descent and find the derivative term, the partial derivative term. All right? So for linear regression, that's pretty easy. Okay? Because it's just a summation of terms, right? So this is from a 4. So if you recall the linear regression one, so this is 1 over m. Okay? So we had 2, right? And what's going to happen is when you differentiate, we have the 2 here, right? Okay, and if you take a look at the cost function up here, what's going to happen is if you differentiate with respect to theta j, this is a sum of theta j terms. So this is theta 1 squared plus theta 2 squared, and so on, right? If you differentiate with respect to j, only one of these is going to remain, and then you differentiate that, there's a power of 2, and you bring that to the power 1. So what's going to happen is you have plus 2 lambda theta j. Okay, and then these 2's cancel, and then what you're left with, so this is d theta, sorry. And then what you're left with is, sorry, so you have 1 over m. Okay, so this is from a 4, and then you have plus. And that's all you're introducing. So this is from a 4. And then you're adding this guy at the end. So you're just adding a single term, regularization. That's it. That's all you're doing. So the only difference between the derivative of the cost function between without regularization and with is just adding this term at the end, lambda over m theta j for that theta j. So if you set lambda equal to 0, it makes sense that you're only considering that portion on the left, which just does regular gradient descent. And then this term here, you add that on top. It's just adding regularization, right? And then logistic regression is pretty much the same thing. It's exactly the same thing. So just move up. So right? Logistic regression is pretty much the same thing. I'll let you figure that out, but it's the same thing. So okay, if you decide to do the math, it's going to be exactly the same thing. Okay, so same. Okay, all right. So finally, now we have this. Let's just modify the gradient descent approach. So The only thing that you're going to change for gradient descent is just adding one more term. So now gradient descent. It's really cool how you just add one more feature to the gradient and it actually prevents overfitting. It's actually quite nice. Gradient descent for linear regression and regularization. Okay, so let's see here. So you've got initialize. Oh yeah, and this is for j equals 1, 2, and so on. Doesn't include 0, okay? Make sure you don't include that. So it does not include j is equal to 0. 1, 2, up to n, and 0 is not included. Okay, so initialize theta 0, theta 1, up to theta n, and then you're going to repeat. So basically, so this is what it's going to, this is how it's going to go. So theta 0. So we have alpha. Sorry. Okay, just want to make sure I got time. Okay, so this is with the, this is just the bias term, so without regularization, and then you have everything else. So this, I'm going to take this guy. Nice, the beauty of copying and pasting. Okay, so just get rid of this. Okay, and then plus lambda over m. Let's see here. So this is subtract, and then here, and then, okay, there's that whole term here. Okay, and then what I can do is I can take this term, and I can group it with this term over here, all right, because they're, they're pretty much the same. And then you have a minus here. So what's going to happen is 1 minus lambda over m, theta j, and then minus, sorry, there's an alpha here. I forgot the alpha. There's an alpha here. So alpha over m. Okay. All right, so this is gradient descent for the linear, also logistic regression. I'm not going to rewrite that. Okay, it's pretty much the same thing. So I have this guy here. So this is just for the bias term. And then I have this one for the rest of it. So the only difference between this and this one is this term here. So for j equals 1, 2, all the way up to n. And that's it. Okay, so that's how you incorporate regularization into the mix. So it's just one additional term. Okay? And that's it. I got one more. I got to do a MATLAB demo just to be sure. But that's it for theory here. Are there any questions? Okay, good. So I'll leave this here, and then I'm just going to quickly talk about, just give you a MATLAB demo. I'm going to demo the optimization toolbox. Okay, so MATLAB demo on optimization toolbox. You unfortunately can't use this for the first lab, but you're going to use it for the next lab to make things a little easier for you. So MATLAB has what's known as an optimization toolbox, and that toolbox is specifically designed to minimize cost functions. So you don't have to use gradient descent. You can totally use MATLAB's toolbox to help you minimize cost functions. All right? So MATLAB has the capability of minimizing cost functions. So you don't have to use gradient descent. The reason why I got you to implement it is because you can see how it's applied to practice. So if you don't have access to MATLAB, if you want to apply it, if you want to do the code on a robot, or if you want to apply it on a C library or something, then you can actually use gradient descent for that, and that's actually pretty cool. Okay, so function, and then uses advanced optimization algorithms. So there's a whole different bunch of advanced optimization algorithms, which I won't cover, but it goes through a whole gamut of different ones. Advanced algorithms to minimize. Okay, The reason why you want to use the optimization toolbox is because you don't have to specify the learning rate or lambda. That's unique to gradient descent. You don't have to do that for the optimization toolbox. All you have to do is just specify the cost at a particular point and the gradient at a particular point, and it'll do the rest for you. Okay, so advantage. No need to specify lambda. Not lambda, alpha, sorry, alpha. Okay, so these algorithms are usually faster than gradient descent too, so usually faster than gradient descent. Okay, the disadvantage is that they're more complex, usually more complex. And they tend to take up a lot of memory too, so it's a bit of push and pull with using the optimization toolbox, but totally use it if you can. Okay, so how do you use this stuff? How do you use the optimization toolbox? So what do you do? So what do we need? Okay, so what you need to do is, first off, you have to define a MATLAB function that will take in a set of parameters, okay? And the output will be what the cost is for those parameters to assign, what the cost would be to use that data to fit those parameters in your data, and then the gradient or the derivative of each term evaluated for those parameters. So what do we need? One, a MATLAB function. Sorry. Oh, come on. Okay, sorry. A MATLAB function that is defined as follows. Okay, so A, the inputs are the parameters, theta, right, as a n by 1 column vector. Okay? And then the outputs, okay? The outputs are, let's see here, the cost, j of theta, right? Evaluated theta, okay? And then 2, the derivative of the cost. So this is just a scalar value, so scalar of the cost for each parameter. So it's an n by 1 vector. So it expects the output to look like this. So you have theta j over theta 0. And I'll give you a demo, of course, don't worry. It looks all gibberish now, but it should be okay. So this is the derivative of j with respect to theta 0, and this is evaluated at theta 0. Okay, don't worry, I still got time. And then this is derivative of j with respect to theta n, evaluated at theta n, of course. Oh, sorry, where is it? Copy, paste. Okay. All right. And then so you need one of those. So you need one and then 2. And you still need an initial set of parameters though. That should be okay. As long as your cost function is convex, then you shouldn't have to worry. Okay, this is n by 1 vector. Okay, so what you're going to do is you're going to use a function called fmin_unc, which is function minimization unconstrained. So use a function called fmin_unc. So this is function minimization unconstrained. So what unconstrained means is that you're considering all possible values of theta in order to get the right cost, to minimize the cost. All right? Okay, so let me just write a couple more things, and then I'm going to give you a quick demo. It's only going to take a couple lines of code. So the function prototype, what it's going to look like, okay, when you define this function in code, okay, what it's going to look like, it's going to look like this. Function, and then rad. Okay, so the output's going to look like this. So this is the cost, okay, and this is the gradient vector. Okay, and these are parameters. Okay. But the thing is, though, that the expected function here, it only takes in the parameters, but you want to incorporate the data too. But MATLAB doesn't like that. It only expects the input to be just the parameters. So if you want to incorporate the data into your cost as well, you have to use what's known as an anonymous function to wrap it all. So, question. Hold on, don't worry. Question. How do we incorporate the data into the cost function? Okay, so use an anonymous function. Got one more slide, and I'm going to do a quick demo. I should be done in a few minutes. All right. So what you need to do is define the cost function normally. Not normally, but define the cost function with the data. So in that case, what you're going to do is you're going to take this, okay, and then you're also going to incorporate the data. So x, y, and then theta. So this is the inputs, and then this is the outputs, right? So input features, and then labels, right? And then these are the parameters here. And then last but not least, all you have to do is just do this. Just do func equals, and then cost function. So x, y, and then theta. So this is what's known as an anonymous function. So you have to declare x and y first. So then what this does is that it will create a function that just takes in one parameter, but it captures the x and y so that you can use it into your cost function, and then you're done. Okay? So let me just do a quick demo for you, and we'll be on our way. Sorry, where am I? Full screen. Okay. All right, so we're here. So let's see here. Okay, so what I'm going to do is I'm just going to do this for linear regression with one variable. So you're going to declare function prototype. I'm going to post this code online, of course. X, y, theta. Okay? And then what you're going to do is, let's see here. So first, first get the total number of examples. Almost done, folks. Okay? And then what you're going to do is compute the cost. If you remember from the previous lecture, it was 1 over 2m times sum, and then theta 1 plus theta 2 times x minus y. And you square all this. Okay, so that was the cost. And then if you want to compute the gradient term, okay, the first one, so create a 0 by 1 or 2 by 1 vector, 1 over m times, and then plus theta 2 times x. Okay, so this would be the gradient for that term. For the, actually no, this is the second one, and then the first one is just with that without the bias. So let me just get this, cut, and then paste. Oh, sorry, and then I don't need this. Okay, and then you end that. Sorry, so this is grad 1. Okay, and then you end. Okay, so you compute the cost, right? You compute the cost that's here, this is linear regression, then you compute the gradient term, so the first and the second, and then you're done. Okay, and now what I'm going to do is I'm going to run through how to run the function, or the minimization. Okay, so basically, first define your data. First define the data. I'm going to use the data that we did from the first class. So 1, 2, 3, and this was 2, 4, 5. Okay. And then what you're going to do is define the optimization options. Okay, so what you're going to do is you're going to use a function which is called optimSet. All right. So what optimSet does is that it creates a bunch of options that the minimizer is going to use, and there's an option which is called grad object, which means that you are going to specify the gradient of your cost function by yourself. If you don't, it estimates it numerically, but we want to specify the gradient ourselves. And then you want to make the maximum number of iterations 100. Okay, so grad opt means that you are specifying the gradient yourself. Okay, and then what you're going to do is create an anonymous function. So cost function and then x, y, theta. Okay, and then now what you're going to do is you're going to call minimizer. So how it works is you have the first parameter gives you the optimal parameters. The second parameter gives you what the cost that the function is evaluated at the minimal and at the optimal parameters. And finally, the exit flag tells you, a status flag tells you how it converged, how it didn't converge, and so on. And then we're going to specify 0, 0 as the initial point, and then options. Okay, so first parameter is the function to minimize. Okay, second parameter is the initial parameters, and then third parameter is the options. Okay, all right, and then finally, and then all I have to do is just plot this. We're done. Okay, so, let's plot the values, all right? Okay, and then I'm also going to generate the line. So going from the minimum to the max, and then we'll also, plot the line as well. Okay, and then B. Okay, so spawns a new figure, and we plot the points, and then also plot the line. Okay. So let's run this. Let's call this linear regression and then optimization, I guess. Okay, so cool. All right. So it tells you that the local optimum was found. So there are different variables here. So if you take a look at the optimal theta, it gives you that the slope was 1.5 and the intercept is 0.66. And then the cost function was evaluated to be 0.0278. And then exit flag of 1 means that it converged successfully. And this is what the figure looks like. So it managed to find the right parameters given what you specified. So that's just a quick demo. I'll make it a little more clear in the next lab, but you're going to be using this toolbox for the next lab, so you don't have to use gradient descent. Okay, thanks a lot. I'll see you next week.